Alright, time for another DraftPhysics.com video presentation. I guess I should have to make an appearance. So there, I did. Alright, so this math and science guy, Jason something or other, keeps making videos, as science presenters do. And so I'm just going to again point out how he's teaching, okay, a fable, or at least it's a story at this point, because he's really not going to explain why he thinks any of this story he's telling has to be believed as the truth or as an accurate description of how the thing works. So lots of people claim to know how magnets work and what magnetism is, and I'd argue that they really haven't allowed those theories to be tested, and that I would argue that there are other theories that are viable explanations and just as good, if not better. That would certainly be the argument as an explanation. And they're given no airtime at all, and this is all just propaganda. And none of these people, as scientists, do anything to encourage any kind of debate, and the audience apparently, okay, doesn't want anybody to be debated, anything to be debated, any conversation to take place that would involve questioning or doubting what has been established as the standard religion. And that's really all it is a standard religion. Its credibility isn't any higher, or there isn't any logical or intelligent reason, okay, to believe that they have gotten to the truth, that they're right on it, that they're just inches away. Yeah, no. Alright, so I'll just jump through this video. It has, it makes statements that I think are easily pointed to and stated how it really doesn't work that way. Okay, that's not really what's happening, and you can sort of know it's not really what's happening. Alright, something like that anyway. So let's hit the play button, see what we get. Probably a commercial. So probably. Alright, back. Alright, so this is a little further on in the video, so we'll go back to the beginning. So the first half he's just doing a lot of iron filing demonstrations, which are great. But he says things that doesn't show in what he's saying. So I mean, here when he starts to draw it, they do this. The field comes out of one end of the magnet and loops around and goes in the other side of the magnet, as if there is some evidence that there's some sort of current flowing. And there's no evidence. Compasses turn to the field. They don't move with the field. So you can't just put a static magnet somewhere and have the dust or the atmosphere or something start moving in the field. The moving field, because there really isn't one. Okay, it's just an artificial placeholder for a description of how magnets turn and what they look like, how they arrange themselves. And so they're basically just drawing, as Faraday did, what the iron filings look like. It isn't really happening. And there's nothing real flowing on these lines. There's no real flow of anything. Okay, they're not arbitrary, but they're an emergent aspect of the underlying function. And so they don't get to the underlying function. Alright, so let's start with the beginning. Just see how he prefaces what he's saying. Okay. How far back is the beginning there?
A few times, but I want to explicitly say.
Oh, no, let's see. This is it's just terrible, all these commercials. Well, that's unfortunate. Apparently I was paused while I drew all that. Yeah, well, starting over. Alright, so yeah, to evade commercials, I guess hit the pause button and that fucked everything up. So anyway, yes, I know about ad blocker. I don't use ad blocker because I want to see what other people are accepting as being part of their presentation. Okay, so these are scientists and they're accepting all kinds of horrible bullshit as being injected into the middle of their science. And so that's just part of their credibility, in my opinion, that they would allow these tacky and cheesy commercials to be part of their science. All right, anyway, so let me play away here. And I'll get to my point again. I don't want to hit pause. No, I want to hit play. See, I want to do all this quickly. I'm always trying to be expedient because I'm trying to do 10 million different things. And you just can't short. You got to take your time and carefully make a video. But it's just, I don't want to do that. Just want to get it done.
All right, now I mentioned before to you that the magnetic field is exiting or coming out of the North Pole and then coming back around and connecting back in through the South Pole.
So again, he said it, I mentioned before, he will say it multiple times in this video, and it's always wrong, and it's just, there's no explanation for how it knows how to do any of that, or what exactly is traveling from here to there, and why there's no current created. Nothing will ever travel from the North Pole to the South Pole in that manner. It won't happen. It's not exactly how it behaves. It's just because there's a certain mathematical connection between magnetism and electricity that they say this stuff, but it really isn't how it works. Okay, it's not a good way to understand what a magnet is doing. In my opinion, not even close to a good way. Alright, so we'll go back to some of Maxwell's drawings about charge, and really charge is the same thing as magnets, right? Magnets have plus, they have attraction and repulsion, and charge has attraction and repulsion. So the two have a huge parallel. And so if you just thought of the magnet as being two charges stuck to each other, a dipole, then you could understand some of this stuff. And if you understood atoms as being tripoles or quadruple poles, or all kinds of having more than one pole, more than one polar dimension, all of this makes so much more sense in terms of being physics, being understandable as a mechanism. Alright, so let's go to the drawing. So you saw him do it, okay? The stuff comes out of the north end and somehow goes into the south end. Well, that's not what's really happening. I don't want to turn that off. I want to turn this on. Yeah, there we go. Alright. Oh, it's one of those days, I guess. Alright, so this is all the crap I already drew. Alright, so magnet. Just think of it, okay? North-south as electron proton, okay, and they're stuck to each other, so it's just a dipole. And if you understood Maxwell's theories and his drawings, what a charge is, okay, if I had an electron and I had a proton, it's basically got these things called lines of force. This is how you can understand it. So I could draw any number, but I want to just make them proportional. They have the same charge, so I put the same distance between them leaving. Alright, but I could use 10 lines, I could use 400 lines, it doesn't matter how many lines I use. And all you really do to say what's the connection between these two things is say how many of these lines intersect the other object. How many of this one's lines intersect this object, how many of these lines intersect that object, and you can decide how, if it was two electrons, how much they repel each other, or if it's an electron and a proton, how much they're going to attract each other. So it's completely dependent, okay, on the intensity of those lines, and those lines just really represent the inverse square law in the sense that the object's radiation is separating in both dimensions. So it's shooting little blobs of paint, you could say, and it's really just, it's shooting out of all points in all directions, and you're really just saying how much paint is hitting this versus how much paint is hitting that, and that'll tell you how much repulsion and attraction there are. Now obviously with charges, you don't have two charges stuck to each other, but it's the same thing. If you did it, if you took the charge model and you just made dipoles out of it, that is, you just stuck an electron to a proton, a neutron, for example, then you could see exactly what magnets are doing, because they're just obeying these rules about this attractive force and this repulsive force radiating in straight line vectors. So if you thought about the magnet as just radiating, okay, now it doesn't do that. It's actually a pattern of radiation. That is, there's a mixture of, from one end it's doing this, okay, electron in the center, then this is the proton lines are hitting here, and then it's a, you know, again an electron line. You know, you could just say it's like a bullseye. And so the south side is sending little bullseyes, okay, that have a dark center, and the north side, the magnet's got the empty in the first part, you know, empty center, and so it's an opposite bullseye. Blue in the center, red in the center, and so they're sending a pattern, but I don't want it too complicated. If you just thought of it this way, okay, they're just lines of radiation coming out of these two ends, and this is obviously the proton radiation, this is the electron radiation, and then you're just saying, well, what if I put another little baby dipole here, okay, with an electron and proton? What's it going to do? And the fact is, it will turn to this field, right? It's going to have it's going to have two kinds of things will be happening. There'll be the force from this proton, let's say, to, is it attracted here and it's repelled here. So it's going to have a certain pressure on it based on its repulsion and its attraction. Same thing for this one. It's going to have an attraction to one and a repulsion to the other. So you have those four lines to calculate, and that'll tell you how this will turn, okay, to the field. It'll be a certain pressure, because the electron type, like I said, they're tied to each other. They have to move as one unit. All right, so that's the little piece of iron. So all the little pieces of iron are going to move, they're going to turn to maximize their attraction and minimize their repulsion. So in this case, you could clearly understand why it would go north, south. The south end would try to evade this south end, so scooting behind the north is going to clearly be encouraged. If it's a little bit crooked like this, well, then the south side can see the other south side, and it's going to say, well, I can see you. I guess I didn't draw that so you could see that. I had to do more of an angle like this. So this south side can see this south side, and it's going to push, repel, so it's going to swing this way. And this north end wants to maximize the attraction, so it's going to move towards. And yes, this direction is towards in this case. There's a huge portion of that vector that is towards the south end. So it's going to turn to face it. So yes, this is what it's going to do. It's going to line up pretty much face to face. But if the further out I go, like I said, the more it sees the other pole, and the more it ends up, this end up being attracted to this end. So it wants to flip more this way. So it starts to turn, and here it's going to be even. Okay, you can sort of understand that. Then it's going to point the opposite direction here. So that's just the compass needle showing you what another dipole does in the presence of this dipole. Now the trick is this magnetism is being induced, so they're not compass needles, they're iron filings, and what they're going to do is they're going to line up exactly the opposite to this magnetic field. Okay, this is going to be the south end and this is going to be the north end, and they're all going to stick to each other and essentially create another magnet here, and then another magnet out here. And you can understand why there's a distance between them, because, you know, quite obviously they're repelling each other. These are all south north, okay, you know, south north, and the original one was north south. So these magnets are all going to repel each other. That's why there's space between them. So yeah, it looks like these are pathways, but they're not. All right, and they're being created by a real straight line vector force, okay, that's emanating from these two foci of the magnet, the south end and north end, the poles. So it's just dipole behavior. So the simplest point I can argue is if they told you magnets are just two charges stuck to each other, and how would two charges stuck to each other behave in this field? Big, strong, giant electron, giant proton versus little tiny iron filing. How is the little iron filing going to behave? The little tiny dipole versus the big giant dipole. And yes, it'll be exactly as the drawing of the field lines. But the field lines aren't these lines. These lines by Maxwell are called lines of force. The ones you use to calculate the strength of a charge are lines of force. They aren't the emergent field lines. So I could say that the strength of the field is the same there, same there, same there, same there, equidistant. And I can create a new line here, but it's not a real line. It's an arbitrary line. The real lines are these lines of force. All right. I think that's enough. So leave us continue, and hopefully I will show you that what they say is happening doesn't show up really. It's not in the experiments. Okay. So we don't need this. And we'll go back to this.
The thing I want you to remember is that all magnetic fields have to form closed circles.
All right, so that's not the field. The field isn't creating a closed circle. The circle is something you're drawing relevant to how strong the field is from the center. So the center's a point source. Obviously, the field lines just become spherical, and when you have a dipole, then they become, a different shape because you have two opposite fields being created.
Right? They don't just emanate from a point.
And the only thing that makes them have any direction is the fact that one side, one target, affects electrons more, and the other one affects protons more. It's just about what the center of the bullseye is.
Point like electric fields do. They form closed loops only.
Okay, so no, the field line, the force is just as radiant, okay, as a charge is, as electricity. It's just as it's flying out into the atmosphere, the world, and it's really just saying the only thing that's going to be affected are dipoles. The only thing this mixed field can do is, the only thing it can detect the field are dipoles. Okay, monopoles can't detect the field because it's a pattern, and they have to match the pattern. Something with a blue center bullseye has to see a red centered bullseye, and then they'll attract, and vice versa. They have to have a pattern match, and a single electron obviously can't pattern match.
Right? And so here's the bar magnet. So that's what we visualize here. So here's another bar magnet into the shape of a cylinder. What I want to do is visualize this field in a three-dimensional shape. Here,
okay, so this is a nice little toy, and what you'll see is it's not doing what he says it's supposed to do, which is it's supposed to move in one direction, and the iron filings clearly won't be doing that.
Is iron filings. We're going to do a lot with iron filings, but here is just a fluid-filled box here, full.
I guess I should try to make this bigger so you can see it better. I know help, Gary. Okay, I can try. Yeah, we can do that. See how it goes.
Full of iron filings.
Ah, I forgot to fix the volume. Damn it. Alright, my bad there. Oh, so there's just so many things I have to do. Yeah, there's like 4. 4 is just too many. I'm getting too old. Too tired.
So with no magnet inside, you can see what's going on here. Let's drop this thing in here and see what happens. We'll drop it in there and look at what happens.
Yes, what you'll see that's happening is there's a whole bunch of stuff moving towards the red end and a whole bunch of stuff moving towards the white end. So it isn't going in one direction. It isn't going from north end to south end. The little filings are sticking to both ends. They're being attracted by both ends, and there's nothing stopping them from getting to the surface of the magnet. So they're not going to be in suspension very long because they're going to move and stick to the magnet. They're not going to create lines for very long because they can move right into the magnet. That's what they want to do. They're oppositely aligned magnets. They want to be attracted. They want to move into the magnet.
There, the magnetic, you can see the magnetic field.
So yes, you can see that these are moving up and these are moving down, and you can see how they're clumping. Is obvious that Yes, these are collecting an equal number of little iron filings. They're an equal number are being collected down here. There is no flow from one end to the other end.
Immediately appear. In fact, it's a little more impressive.
I mean, you can just see them. They're moving right into this end. They're moving right into this end. All right.
So if I close it off here, and you can see it's sort of attracting inside of there now. And if I give it a nice little shake, and I'll try to get the angle with a couple of different cameras. So there's sort of...
So you can see, so he's got this stuff swirling in a direction because of the way he shook it. But once that swirl stops, but you can already see it's clumping at this end. And what are they doing? They're all sticking out. And how are they sticking out? Well, separated from each other because they're all opposite magnetized pieces. So each one of those little threads is a same magnetism. They're all opposite the original magnet, and they're all repelling each other. So they're all creating little points sticking out that are separated by distance because they're all repelling each other. They'd all stick right to each other if they could flip again and then stick to each other, but they can't flip because they're opposite of the first magnet. The original magnet created all the other magnets, and all the other magnets have already turned to optimize their attraction to the first magnet. So they're all repelling each other. Each one of these little threads in here are all repelling each other, and that's why you have this illusion of lines. It's because they're just repelling each other. They're lined up to be opposite magnets to the original magnet, and they're obviously all repelling each other. So yeah, it looks like a bunch of lines, but it just looks that way. Okay, it has nothing to do with anything moving in those lines. Those lines are completely not related to the actual function. They're just a very useless side effect. They're just a side effect that gives you confusion about what's really happening, which is there's a proton end and an electron end, and they're both doing what protons and electrons do, okay, which is attract the other electrons and repel protons. So everything's turning. The other dipoles here are turning to meet the south end. The ones on the other end are turning to meet the north end.
The side view there, we kind of let it go so you can sort of see that. And then we'll do it with sort of the top view there.
Yeah, he doesn't leave it alone very long. So the top view is good later.
And so you can see...
Fuck. Yeah, I can't believe so many. God, I can't believe he has this many commercials. Whoa. I'm recording? I thought I just paused. Ha! Microsoft commercial. Who knows if this video is in one piece or not. It looks like it's way too small. 22 minutes. I think I've been talking a lot longer than that. I really hate this. I really have to get this right. So you probably missed some other chunk of this, which is really disappointing. But anyway, whatever. Let's just play along. Shit.
They can no longer pick up anything else because it has to be close to the parent magnet in order to...
Yes, and it's again, you know, all that magnetism and all the iron filings is induced magnetism. So obviously, the effect is being reduced by that induction. So now the magnet has essentially used its capacity up. It can't make more magnetism because it's already used up what field effects it can create by inducing magnetism in all of those other objects.
To be magnetized. So the effect does wear off. You can't build these things forever.
Right, okay. We don't need that. So move ahead.
Maybe that far away that you can...
Alright, so he did it again. The field lines, you can sort of understand. You can see that these lines, these separations here are bigger than the separations out here. So, I mean, again, it just totally, it's the opposite of what he says the rule is, so not really demonstrating that this theory they have has anything to do with the truth. And again, these lines are just arbitrary. They're just a consequence of what happens when you put dipole boats, okay, next to the dipole ocean liner. They're going to align with each other in this opposite manner. The little boats are all going to go that way, and the big boats going that way.
You really see the field very, very, very clearly. And check it out. As you move it around, it's so neat to watch the field sort of propagate through the iron filings.
Neat. I love neat stuff. So again, I guess he's See, they intend this to brainwash children, sorry, to, frankly, molest their intelligence. This is just, in a sense, a kind of molestation of intelligence, because you're just starting kids off with wrong ideas and wrong perceptions. And it's so overt in the sense that the little clever kid will say, but that doesn't show what you're saying. How come you're saying it?
In fact, that's so cool.
That's not what it's showing.
So we start over here this time, and let's just sort of race through and watch the magnetic field propagate through and affect the iron filings.
Yeah. So it's not the magnetic field propagating through. It's just you're leaving the finger, the footprint behind, because these things aren't going to be able to move anymore because you took away the magnet. There's very little current inside, so they're just going to stay where they are.
They're above, like that. All right. Now, if you remember the really, really, really strong magnet, we had a hard time visualizing because it was attracting so kind of violently, for lack of a better word. So we'll do the same thing. We'll see how fast it happens. Boom. It's just done.
Yeah, and so you can sort of get the idea that this is about a straight line force. And again, the catch is that all these little lines represent a new magnet. All of these are magnets, and they have an opposite. Again, like I said, they're going to have an opposite polarity to each other because they all have the same magnetic orientation, and that's why they look like little hairs, that don't combine.
Tracks it so fast you can't really see it. So what we can do to visualize it a little better is, because we couldn't really see it better before, we can just keep it separated from...
Right, and even when you keep it separated, it still doesn't show any of this going out one end and going in the other end. None of that happens.
The top, like maybe this far away, and it's still starting to suck it in from...
Yeah, it's right. It's what it's basically doing, right? So again, his demonstration doesn't fit the theory.
Through the table and back through the bottom, so we're not really able to see. You would have to look from the side to be able to see the profile. Maybe we'll try it.
Right, so this is the part where they start saying it makes hyperboreloids, of magnetic field. And again, it can't do any of that stuff. It's just a symptom. When you make a very thin magnet, with a north side and a south side, but it's wide, obviously that's going to create a whole different kind of orientation. There's much more space, less space. The magnet has to decide 50-50 which way to flip. So yeah, you're going to get a different pattern, but it really doesn't have anything. It doesn't do anything to the simple argument that these are just lines radiating, and one side is radiating red, the other side's radiating blue, you could say. Now, it's not strictly red and blue, but I'm just saying that the two are different. Blue-centered bullseye versus red-centered bullseye. One side is radiating a bullseye pattern that has a red center. The other side's radiating a bullseye pattern that has a blue center. And when a dipole, sees the red-blue, it does one thing, and when it says blue-red, it does another. It does the opposite. Jump ahead a little.
Going around very, very weakly down.
See, again, he just talks about a field going around, and there's no evidence of it. Just about zero evidence of any field going around. And clearly the magnetism isn't very consistent. There's little hot spots here and there, where the polarity is a little confused.
Connect to the other side as well.
Oh, geez, ads on top
What
of
if you could get rid of your kitchen garbage at the push?
On top of ads, on top of ads. Shit. Oh, God. It's terrible. Anyway.
This one here, we'll go first from the top view here. What does our little magnetic plate here show us? Of course, this is a lot stronger, so we can see the flux.
Yeah, you can see these giant separation between these lines. Giant separations between the lines. Right? Little tiny separation way out here. So again, just completely the opposite of what he attempted to argue, because he's really not connecting Maxwell's description of attraction and repulsion as created by charges to magnets, which are really just dipoles. And they're dipoles of charge, essentially. They can be understood as just being that simple. They're simple dipoles. You can have big giant ones, you can have little tiny ones. Alright, so we don't need more of that, I guess.
Turn the test equipment on. We're going to hook up an electric current through a wire, and we're going to see that the wire that's passing the electric current generates its own magnetic field surrounding the wire.
Right, it's a very weak magnetic field, so he has to use, few hundred watts of electricity to create a feeble magnetic field.
The compass, when we bring the compass close, we can see that as I move the compass around the wire, it is now affected by the magnetic field. We'll come on this side. You can see as I go around.
Yeah, so really
here, it's
poorly affected, okay? I mean, north-south was actually this direction. He's not showing much of a deflection, blah, 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 blah. So that wasn't a very good experiment. Now he's going to use an electromagnet for a different... Oh, turn off all ads. I bet that's not what's going to happen.
curling in a circle around the wire. All right. Okay, now we have what we call an electromagnet. So this is a fancy-looking device, but basically what it is a coil of wire.
Right. He doesn't use both of them for whatever reason. He just uses one, and this one actually induces magnetism in the other one, so it kind of defeats his purpose in some ways. I mean, it just kind of damages the demonstration. So he's just showing that, okay, look, this is a 6-volt wire arrangement. You know, you put more than 6 volts in, it starts to get hot.
And see if we can get it to attract there. And as the current goes up, the magnetic field is going up, which is concentrated inside this coil. Let's see.
Right, and why is it concentrated inside the coil? See, I would argue that's a whole nother subject. It's quite interesting in the sense that what you're concentrating the field by doing, the wire is doing, is it's reflecting the field back and forth inside of the coil. The coil is basically creating a trap for the charge. And now the charge can't get out of inside of that coil. And so you're magnifying the energy, but you keep reflecting it back and forth. But anyway, that's a whole different subject in some respects. Okay, so here he's using it.
Now the next thing I'd like to do is turn it sideways and see if we can get a profile view of what the magnetic field is doing. All right, let's try it first with our little plate here. We're going to turn the voltage on up to 6 volts. That's about or 5, let's do 5.5 volts, about 2 amps, 2.2 amps, something like that. So a lot less than what we had before. Here I'm going to put my little thing down here. And you can see, I can't get it too close, but you can see the magnetic field appearing right here. In fact,
yeah, you see it going here, and that's about it. And the rest of it, again, is just pointing towards the poles of the magnet. So, all right, so this is... well, this is a little bit interesting, just turning it on and off at different speeds and how much, how responsive the iron filings are. That is, how quickly they lose their magnetism is sort of surprising in the sense that it's really quick. I mean, you can have a pretty fast frequency.
And we can just see it going much, much, much faster. All right? And let's go over here, and let's drop it now. Beating heart, super fast beating heart. All right? How far can we go? I actually don't know. 0.1, let's go 0.05, I guess. 0.05, that's cutting it in half again.
I guess all these commercials buy the equipment, blah, 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 but it's just ads, commercials.
Let's see what this looks like. Seconds. Whoa, check it out.
Whoa, check it out. This guy was actually a NASA scientist. Anyway, so here's the picture from before. Should be from before anyway. You can't see it, but there it is. Okay. And obviously this is an electrical effect in the sense that one side of the magnet pushes electrons, the other side attracts electrons. So you can sort of understand that, yes, there will be an effect on electric circumstances from one end. And so you can draw that by saying the north end is out and the south end is in, but that's a metaphor, or it's a very disconnected comparison because it's not doing that. Yes, it's attraction and repulsion. Yes, electrons repel electrons. North ends repel electrons in principle more, but they only repel the electron end of a dipole. Has to be a dipole to see the polarized field. A monopole can't see polarization. Alright. So this is the wiring diagram.
Terminals, and we ran an electric current through there. Now, for the purpose of this example, let me pretend that the electric current, or the current, I should say, is flowing up. I'm going to talk a little bit more about current in a second.
So this is just the right-hand rule, which way it turns, and this just, again, has to do with which end is positive and negative in terms of electrons versus protons, and how electricity travels through a wire in terms of changing how the atoms look. So it's really just about changing how the atoms look. The atom could have an electron on the outside, an electron in this position. I can put an electron here, I could put an electron here, I could put an electron here. Obviously, if the electron is in this position, the atom's going to look very negative. If the electrons are in this position, it's going to look positive because you can see the nucleus. So I can just make that simple argument that all you're really doing is changing the orientation of the atoms, electrons, and protons, and basically turning each atom into either looks like a proton, looks like an electron. And it's that pattern that some other dipole can see. Alright, so we won't get into all that stuff. That's a whole separate subject about how magnetism connects to electricity. But they're forcing it. You can see he's forcing the connection by, talking about these field lines having some sort of connection, and they don't. The lines of force are the only things that matter. Alright. So I think that's enough, and as this video is broken. I'm very disappointed if that whole piece in the middle is missing. Damn. But anyway, if it is, it is. Alright. So, till the next time and such, I have to... yeah. I have to figure out some way to make it very clear when it's recording and not recording, because it's not clear enough. Yeah, it's some sort of beeping sound, right? I'll get one of those backup lights, beep, beep, but that'll probably be annoying, right? But if it only beeped when it was paused, that would work, right? So yeah, they should have a little button that makes it beep when it's paused. And then I know I was paused. Okay. Oh, there, I solved it. That's a feature they should add. Alright, anyway. Yeah, that's enough for video. So I have to get rid of stuff, I guess. I can get rid of this. And then I can get rid of me. Alright, so anyway. So this has been another DraftPhysics.com. Or debatephysics.com video presentation, and there will be no constructive counter argument provided in any form whatsoever, because that's science. Good science is ignore everything and just preach your fable. Yeah, that's it. Okay, anyway, until the next time and such and so forth and whatnot. Blah, 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 blah.